Hi there again. This is Unit 2 of the Hugging Face Deep RL course. I'm going to do a read-through. So this is Introduction to Q-Learning. In the first unit of this class, we learned about reinforcement learning, the RL process, and the different methods to solve an RL problem. We also trained our first agents and uploaded them to the Hugging Face Hub. In this unit, we're going to dive deeper into one of the reinforcement learning methods, value-based methods, and study our first RL algorithm, Q-Learning. We'll also implement our first ML agent from scratch, a Q-Learning agent, and we'll train it in two environments. Number one, Frozen Lake v1, non-slippery version, where our agent will need to go from starting state S to the goal state G by walking only on frozen tiles and avoiding holes. Number two, an autonomous taxi, where our agent will need to learn to navigate a city to transport its passengers from point A to point B. Awesome, sounds good. So here's some pictures, here's some holes, and here's a taxi picking up a person, probably has to go to this building. And a video, or a GIF. Great. Concretely, we will learn about value-based methods. We will learn about the differences between Monte Carlo and temporal difference learning, and study and implement our first RL algorithm, Q-Learning. This unit is fundamental if you want to be able to work on deep Q-Learning, the first deep RL algorithm that played Atari games and beat the human level on some of these, Breakout, Space Invaders, etc. So let's get started. What is RL? A short recap. In RL, we build an agent that can make smart decisions. For instance, an agent that learns to play a video game, or a trading agent that learns to maximize its benefits by deciding on what stocks to buy or sell. Here's a picture of a very familiar RL loop. There's an agent, can take some actions in an environment, and the environment returns a state and a reward. To make intelligent decisions, our agent will learn from the environment by interacting with it through trial and error, and receiving rewards, positive or negative, as unique feedback. Its goal is to maximize its expected cumulative reward because of the reward hypothesis. The agent's decision-making process is called policy pi. Given a state, the policy will output an action or a probability distribution over actions. That is, given an observation of the environment, a policy will provide an action or multiple probabilities for each action that the agent should take. So the policy pi, the agent's brain. Policy pi is the brain of our agent. It's a function that tells us what action to take given the state we are in. So it defines the agent's behavior at any given time. So look at the state, I'm a unicorn, and there's a coin and two very angry octopus, and then the policy pi will take that state and produce an action for me, or a recommended action. Our goal is to find the optimal policy pi, aka a policy that leads to the best expected cumulative reward. To find this optimal policy, hence solving the RL problem, there are two main types of RL methods. Policy-based methods train the policy directly to learn which action to take given a state, and value-based methods train a value function to learn which states are more valuable, and use this value function to take the action that leads to it. Okay, so as we learn this, we're going to have to learn what a policy method, and we're going to have to learn what training the policy directly means versus training the value function. So keep that in mind for later. Two approaches to find optimal policy pi. Policy-based methods train the agent to learn which action to take given a state. Value-based methods train the agent to learn which state is more valuable, and then, using this information, take the action that leads to it. So I think intuitively we are, at least for me, it's not very clear what the differences are, because it seems like for the policy-based methods, we still need to know the value of certain states. So it seems like the way it's defined, it doesn't really talk about the value yet. In this unit, we'll dive deeper into the value-based methods. Perfect. There's two types of value-based methods. In the value-based methods, we learn a value function that maps a state to the expected value of being at that state. So here's value-based methods. The value of the state is the expected discounted return that an agent can get if it starts in that state and then acts accordingly to our policy. So this is a very familiar picture of, discounted rewards, where this reward is discounted by some gamma, and then we add up all these rewards, and that becomes the value. Perfect. The value of the state is the expected discounted return the agent can get if it starts at a state and then acts accordingly to our policy. But what does it mean to act accordingly to our policy? After all, we don't have a policy in value-based methods since we train a value function and not a policy. Remember, the goal of the RL agent is to have an optimal policy pi. To find the optimal policy, we learned about two different methods. Policy-based methods, directly train the policy. In this case, we don't have a value function. And it seems like it's missing a bullet point, or maybe we'll talk about it next. Okay, so we'll talk about it next. Two approaches to finding an optimal policy, pi. Policy-based methods, where we train directly the policy. Our policy is a neural network with no value function. So the policy takes the state as an input and outputs what actions to take. Deterministic policy, a policy that outputs one action given a state, contrary to a stochastic policy that output probability distribution over actions. Consequently, we don't define by hand the behavior of a policy. It's the training that will define it. Okay, so that's a little bit more information about policy-based methods where we don't have a value function, and the training. The policy here will be a neural network, and the training will define what the policy is. As we get more information, we'll learn more about what that is. So a value-based method. Indirectly, by training a value function that outputs the value of the state or a state action pair, given this value function, our policy will take an action. Since the policy is not trained or learned, we need to specify its behavior. For instance, if we want a policy that, given the value of a function, will take actions that always lead to a big reward, we'll create a greedy policy. Okay, so two approaches to find an optimal policy pi. Value-based methods don't train the policy. A policy is a function defined by hand. Instead, train a value function that is a neural network. So, given a state, we have this Q state. It was a table before in one of the diagrams, and then it creates the values for these state action pairs, and then we have this policy that we define by hand, and it returns an action, right? And one example policy is a greedy policy where whenever you find the highest, or whenever you find any valuation of these state action pairs, you always take the highest one, right? So the greedy policy here in their example, assumes no exploration. We're only taking the thing that we found to be most valuable. Yeah, it says right here, our predefined greedy policy selects the action that will yield the highest value given a state or state action pair, right? So state action pair, this is the first time we're hearing about state action pairs, and I'm sure I'll define it later. Consequently, whatever method you use to solve your problem, you will have a policy. In the case of value-based methods, you don't train the policy. Your policy is just a simple pre-specified function. For instance, a greedy policy that uses the values given by the value function to select its actions. So the difference is, in policy-based methods, the optimal policy pi is found by training the policy directly. In value-based methods, finding an optimal value function, denoted Q star or V star, we'll study the difference after, leads to having an optimal policy. So the link between value and policy is there's argmax Q star of these parameters S and A, and S presumably being state, and A is the action. So I think this is maybe something that we saw above, where this is the state and the action pair. Right, so finding an optimal policy leads to having, finding an optimal value function leads to having an optimal policy. In fact, most of the time in value-based methods, we'll use an epsilon greedy policy that handles the exploration-exploitation trade-off. We'll talk about it when we talk about Q-learning in the second part of this unit. So, we have two types of value functions. The state value function. We write the state value function under a policy pi like this. So, two types of value-based methods, a state value function, where the value pi, so the value of this optimal policy of the state is equal to the expected return of the same pi, uses the policy to choose its actions over time steps, and yeah, this g is the expected return, so the g is the I believe the g is the cumulative expected return from above. I'll have to double check that. For each state, the state value function outputs the expected return if the agent starts at that state and then follows the policy forever afterwards for all future time steps. Okay, so this is one. And then the second one, or this is a diagram, the state value function. So calculate the value of each state. So assuming that you have these 9 possible states that you can be in. Here is a detour. This path goes directly to the g's. We find the value of that. So presumably each step is -1. So as you move further and further away from the g's, the value of being in that state is -1 for each one of these boxes. So if we take the state with value -7, it's the expected return starting at that state and taking actions according to our policy. So right, down, right. Okay, and then the second one is the action value function. In the action value function, for each state and action pair, the action value function outputs the expected return if the agent starts in that state and takes action, and then follows the policy forever after. The value of taking action A in state S under a policy pi is this formula, right? So the difference between this formula and the one above, it's still Q. So it's this one was the one above, the state value function. It's the action value function, right? So here, instead of V, it's a Q, and it's a Q pi, and this is the state action pair, S and A, whereas the state value function only had the S, and this part is roughly the same. This is the expected return of this pi, given the agent starts at this S and chooses this action A. So for each state and action, the action value function outputs the expected return if this agent starts in that state and takes the action and then follows the policy forever after. Okay, great. And here's another picture. Calculate the value of the state action pair. We didn't fill all the state actions pairs for the example of state. Okay, that's fine. Okay, sure. We see. Oh, I see. So this X means that it's breaking up this square into 4 different parts: left, up, right, down, and I believe the numbers are in the parts where that's where the action is, right? So this is the state here, the action is right. This is the state here, the action is right, down. You see this -4 is in the lower 4th part of the square. -3 is here, is down as well, and then right. We see that the difference is in a state value function, we calculate the value of a state as t. In the action value function, we calculate the value of the state action pair, st and at, hence the value of taking that action at that state. So here they didn't fill in, for example, in the state going up, or going backwards, or going downwards, it looks like up and downwards would be blocked by a wall, but maybe going, I don't know, but at this state, they could definitely have gone down. They could have gone forward and then back, but they're only calculating, this step, at least in this diagram. So there's 2 types of value-based methods. State value function calculates the value of the state, and the action value function calculates the value of the state action pair. So no, we didn't fill all the state action pairs for the example. Yeah, so we saw that already. In either case, whatever value function we choose, a state value or action value function, the return value is the expected return. Okay, however, the problem is that it implies that to calculate each value of the state or state action pair, we need to sum all the rewards an agent can get if it starts at that state. This can be computationally expensive process, and that's where the Bellman equation comes to help us. Okay, so yeah, like starting at each one of these states, the question is, do you have to run your simulation from here all the way to this cheese, and then from here all the way to this cheese, and then from here all the way to this cheese, or from here all the way to this cheese? Or is there some optimization that can help us reduce the computation, right? So given this state, you could see that maybe that's a very obvious problem if that's your approach. If your approach is to, at every one of these squares, and there's 9 squares here, do a 9 times calculation of, this thing. And maybe the Bellman equation can help us here. So the Bellman equation simplify our value estimation. So the Bellman equation simplifies our state value or state action value calculation. So with what we have learned so far, we know that if we calculate if we calculate the value of the state, we need to calculate the return starting at that state and then follow the policy forever after. The policy we define in the following example is a greedy policy. For simplification, we don't discount the reward. So to calculate the value of the state, we need to calculate the sum of expected rewards, hence. So, here's an example of what a path would look like, where each step is a -1, right? Because, this is a time-based task, and to calculate the value of state 1, the sum of rewards, the agent started in that state and then followed the greedy policy, taking actions that lead to the best states for all possible steps. Then to calculate the value of state of time plus 1, so t plus 1, we need to calculate the return starting at that state, right? So starting here. So this is the, So we have to calculate this one. To calculate the value of state 2, the sum of rewards the agent started at that state, and then follow the policy for all time steps. So you may have noticed we're repeating the computation of the value of different states, which can be tedious if you need to do it for each state value or state action value. Instead of calculating the expected return for each state or each state action pair, we can use the Bellman equation. Hint, if you know what dynamic programming is, this is very similar. If you don't, no worries. The Bellman equation is a recursive equation that works like this. Instead of starting for each state in the beginning and calculating return, we can consider the value of any state as the immediate reward, r of t plus 1, plus the discounted value of the state that follows. So gamma times the value of state of t plus 1, right? So the Bellman equation is this, the value of the state, expected return of the immediate reward, so r of t plus 1, plus the discounted value of the next state, right, given this state. So instead of doing that whole process where we go through, all of these squares, we do the immediate, the immediate reward that we get, plus the expected value of that next square, right, and that's the value of this square. So the value of square of here at t0 is the reward at t plus 1, and then the expected value of that position at t plus 1, right? And, because this position's in the future, we still have to multiply it by some discount value. If we go back to our example, we can say that the value of state 1 is equal to the expected cumulative return if we start at that state. Okay, so to calculate the value of state 1, the sum of rewards if the agent started in that state 1 and then follow the policy for all time steps. So this is equivalent to the value of the state equals the immediate reward of r t plus 1 plus the discounted value gamma times the value of this next state. Right. So here is the original example where we have to do this calculation across these, 1, 2, 3, 4, 5, 6, the 6 steps, and we're changing it to, instead of those 6 steps, we're considering the value of the box of t as these two other factors, right? The reward plus the discounted value of the next state. Now, if we already know that this discounted value of the next state is -5, then it makes our job a little bit easier, and we have have this -1 from this reward, and then we have this -5 here. And here the gamma is 1. For simplification here, we don't discount the gamma, so it's -1 plus 1 times -5, which is -6. In the interest of simplicity here, we don't discount, so gamma equals 1, but you'll study an example with gamma equals 0.99 in the Q learning section of this unit. Yeah, that just changes the calculation, but it's not a big deal. The value of, state plus 1, okay, yeah, so it's the same equation. Yeah, the gamma is it's an interesting concept, because if gamma is 1, that means that all rewards in the present are equal to all rewards in the future, and there's no discounting factor. So it's like the longest term view that you can take. If you were the agent, what is the longest term view that you can take? The longest term view is that like $1 today is actually the same as $1 in the future. And for simplicity, that's how the equation is done here. So to recap, the idea of the Bellman equation is that instead of calculating each value as a sum of expected return, which is a long process, we calculate the value as the sum of immediate reward plus the discounted value of the state that follows. Yeah, so the natural question here is, well, where did I get this one, right? So I know that this is -6 because I did this long process. You give me the Bellman equation, you say that I can get rid of these boxes here, and I can only focus on this one. And then the natural question is, well, sure, but where did I get this state? Well, this one's probably calculated from this one, right? It's probably the reward of this one plus this, the state of this, the value of this state. Well, where did I get this one? Well, it's probably the value of this state plus this reward. And this is the reward plus the value of that state. So you eventually get to this ending point, right? So it seems like for the Bellman equation, this ending point really matters, this terminal state. And then when we have this terminal state, we start working backwards up the chain. And instead of duplicating the computation, all of these boxes have only been computed once in this example. And it is a linear operation versus what we had before, which was a n² operation, where for each state, we were, at least in the previous section, calculating the entire maze. Great, so before going on to the next section, thinking about the rho of gamma and the Bellman equation, what happens if the value of gamma is very low? What happens if the value is 1? What happens if the value is very high, such as 1,000,000? Right, so we talked about this before, like if you see yourself as the agent and gamma is 1, then $1 for you today is the same as $1 10 years from now, right? And it can, maybe if you lived 1,000 years, that's not a big deal, but if the world is uncertain and $1 10 years down the line is actually $1 plus the risk of me disappearing, the risk of the dollar being inflated, the risk of you no longer using dollars for your payment, then in that world, it's a little bit different, right? And what happens when gamma's really small? Then when gamma's really small, then nothing in the future matters. I only care about what's right now. I have the most impulsive, short-term thinking version of myself ever, right? So what if I gave you $1 today, but $1 million in 2 minutes? Well, if your gamma is so low that the $1 million is completely discounted, then you don't care about the $1 million in 2 minutes. You want that dollar right this second. You can't wait to 2 minutes, right? And then the opposite, if it's very large, well then, only the long term matters. In fact, nothing immediate matters at all, right? So if gamma is very large, what if I gave you $1 million right this second, but in 10 minutes, I'll give you $10. But the gamma is $1 million. So for you, internally in your brain, the reward of that $10 in 10 minutes is $10 million. It's warped. It's probably not mapped to reality. And, typically you don't see any discounted cumulative sum functions have 1 million as their gamma. This would make no sense. Imagine if you did that for a business. Like a dollar. Anyway, you get it. So I'm going to stop the video here. There's a lot of good sections here, and then I'll start again with the next one.